This video is part 2 of a review of Unit 7, which is all about the applications of the theorems of calculus. These problems will be considered calculator active, so we will use our graphing calculator as needed. If you haven't seen part 1 yet, I will try to put a link in the upper right hand corner, or you will find a link in the description. For problems 5 through 7, we are given the graph of function f with geometric areas as shown. We also have the integral defined function g of x shown here. For number 5, we need to write one word to complete each sentence. So g at 5 is positive, negative, or 0. Well, g at 5 just means plug in 5 for x right here. So we will have the integral from 2 to 5 of f at t dt. So here is 2 and here is 5. This integral is going to be the area between the x-axis and the curve between 2 and 5. So we're talking about area B. However, because this is below the x-axis, the area will be considered negative. So g at 5 is negative. For the next problem, we will use the second fundamental theorem of calculus, specifically the common case, which is the one we get to use when the lower limit of integration is a constant and the upper limit is just x. In this case, g prime will simply equal f of x. That's the situation we have here, the common case. So just remember that g prime will equal f of x. So g prime at 5 will just equal f at 5. This is the graph of f. So the value of f at 5 is 0. Since g prime of x is equal to f of x, then g double prime of x will equal f prime of x. So in that case, g double prime at 5 will equal f prime at 5. This means the slope of f at 5. So here is f at 5. The slope right here, we don't know exactly what it is, but we can tell that it is positive because it is increasing from left to right. So g double prime at 5 is positive. Number 6, find the absolute maximum value of g on the closed interval from 0 to 8. So we will need to do a candidates test. The first step of making a candidates test for function g is to find the critical values of function g. That means we need to find where g prime is equal to 0. But we don't have a graph of g prime, we have a graph of function f. Luckily, we know that g prime is equal to function f. So we need to find where g prime, which equals f, equals 0. Where does function f equal 0? Let's just scroll up and take a look. Function f equals 0 here and here. So the critical values are 2 and 5. Make sure you label the candidates test like this. For the x values, we will be sure to use both endpoints 0 and 8, as well as the critical values that we just found. So let's find g at 0. Remember that g of x is the integral from 2 to x of f of t dt. So g at 0 will be the integral from 2 to 0 of f of t dt. This yellow area represents the integral from 0 to 2. However, we want the integral from 2 to 0. So normally this area would be considered positive, and specifically positive 2.1. But because we are integrating backwards from 2 to 0, then it will be a negative 2.1. The value of g at 2 will be the integral from 2 to 2 of f of t dt. Of course, this will be 0 because there is no area under the curve between 2 and 2. g at 5 will be the integral from 2 to 5 of f of t dt. Let's take a look at the graph. The integral from 2 to 5 is this yellow area b. Because b is below the x-axis, this will be considered a negative 3.8. For the value of g at 8, we must find the integral from 2 to 8 of f of t dt. The integral from 2 to 8 is the net area from 2 to 8. That will involve the area b and the area c. Because b is below the x-axis, this is considered a negative area. C above the x-axis is positive. So when we combine these, we're going to have a positive 5.7 minus 3.8. That turns out to be 1.9. We were asked to find the absolute maximum value, and the maximum value is right here. For our summary statement, we say g has an absolute maximum of 1.9 at x equals 8. See candidates test. Number 7. Show that g must have at least one 0 on the open interval from 5 to 8. When they start asking us to show that something exists, that's a clue that we will probably need to use one of our 5 existence theorems. There's the intermediate value theorem, the extreme value theorem, Rolle's theorem, the mean value theorem, and the mean value theorem for integrals. So which one are we going to use for this problem? First of all, what does it mean for g to have a 0 on the interval? A 0 means that there is some value, let's call it c, where g at c is equal to 0. The extreme value theorem has to do with the existence of a maximum or a minimum. That has nothing to do with what we're looking for, so that one is out. 2 of the theorems deal with the derivative of a function. So in this case, we just want g at c, not g prime. So anything that talks about the derivative, and we would think g prime at c, is going to be out. So Rolle's theorem is out, and similarly the mean value theorem is also out. It talks about f prime. The only 2 theorems that talk about the original function f at c, or in this case g at c, are the mean value theorem for integrals, or the intermediate value theorem. Let's try the intermediate value theorem first, because this one is more straightforward. For the intermediate value theorem to apply, 2 preconditions have to be met. First of all, the function in question has to be continuous. In the setup of the problem, we are told that g is a continuous function. So far, so good. The second precondition is that if we want to be sure that the function will equal, let's say, k somewhere, then we have to have a value of the function that is below k and a value of the function that is above k. In this case, we are trying to guarantee that the function g will equal 0 somewhere. For the intermediate value theorem to apply, we need to have a value of g that is below 0 and a value of g that is above 0. Well, look back at our candidates test where we came up with a bunch of values of g. Before we look too closely, remember that we are only interested in the open interval from 5 to 8. And oh look, the last couple values on the candidates test are in that interval. To show that g must equal 0 somewhere, we need a value below 0 and a value above 0. And that's exactly what we have. So we can go ahead and use the intermediate value theorem. We have to start off by stating the preconditions. So since g of x is continuous, and g at 5 is less than 0, which is less than g at 8, in other words, since we have one value below 0 and one value above 0, optionally we can say by IVT, but this statement is not required. And finally, the conclusion. There is a c in the interval from 5 to 8 where g at c is equal to 0. For number 8 through 10, a particle moves along the y-axis on the closed interval between 0 and 8 seconds. Its velocity v in meters per second at time t, which is in seconds, is graphed here. At time t equals 0, the particle's position is y equals 7 meters. Number 8. Find the particle's average velocity on the interval from 0 to 5. We have learned two different formulas that have the word average in it. One of them is average rate of change, which is this formula. The other one is the average value of a function, which is given by this formula here. So we have to be very careful when you have a question which is asking for an average something. Am I asking you for the average rate of change or the average value? If I want the average rate of change, I pretty much have to say the words rate of change. Otherwise, it's the average value. So if I say, here's a function for temperature, and then I ask, what is the average temperature? That means the average value of temperature. If I give you a function for velocity, and I simply ask, what is the average velocity? That means the average value of velocity. And that's what we have here. Find the particle's average velocity. That means the average value of velocity, not the rate of change. So here's an expression for the average value of velocity on the interval from 0 to 5. In the numerator, we need to calculate the integral of velocity from 0 to 5. But we are given a graph of velocity. So the integral of velocity will be the area between the curve and the x-axis between 0 and 5. From 0 to 5, we have this yellow area and this blue area. The yellow area will be considered positive because it is above the x-axis, while the blue area will be considered negative. The yellow area has a value of positive 40, and the blue area is a negative 20. That's a net value of 20. So we have 20 divided by 5, which is 4. Remember, we are talking about the average value of velocity. So the units will be the units of velocity, meters per second. Number 9, find the total distance traveled by the particle from t equals 0 seconds to t equals 5 seconds. The formula for total distance is the integral of the absolute value of velocity. So it's going to be very similar to what we just did in the numerator, but we will treat the blue area as positive as well. So the total distance will just be 20 plus 20 plus 20. That's 60 meters. Number 10, at t equals 0, the particle's position is y equals 7 meters. Find all other times on the interval from 0 to 8 when the particle's position is 7 meters again, or explain how you know that there is no such time. If the particle starts off at the position of y equals 7 meters, and later it's going to be at the same position again, 7 meters, what will be the net change in position? 0. So we're looking for time when the net change in position is 0. The integral of velocity from 0 to t will be the net change in position from 0 to t, and we want this to equal 0. If we want the integral of velocity from 0 to t to equal 0, that means we want the net area under the curve from 0 to some value to equal 0. So we have illustrated the net area from 0 to 5 so far. And so far, this net area is positive 20. So we need to cancel out the extra 20 with a little bit more negative. So if we go over one more space, all right, if we go over to 6, that gives us an extra negative 20. Now the positive area is completely canceled out by the negative area, and we have a net area of 0. So the answer is going to be t equals 6, because this is the value at which we have a net area of 0. Side note, notice that I'm using x's inside this integral defined function. Whenever you have an integral defined function, meaning we have a variable as one of the limits of integration, we need to use a different variable in the integrand and in the dx. So I already used the variable t, so I just picked a random different variable. I could have used s or really any variable, just something other than t. For our final answer for number 10, this is all the work that needs to be shown, because this would be read: the net change in position from 0 to t is equal to 0 at t equals 6 seconds. That was the most efficient way to set up the problem, but here's another way to look at it. We know that the end position will equal the start position plus the net change in position. In this case, we want the end position to be 7 meters, so I can just put a 7 right here. We are told that the start position at time t equals 0 is also 7 meters. So the net change in position from 0 to t is going to be the integral of velocity. Except let me use x's instead of t's because of what I mentioned earlier. I can now solve this equation by subtracting 7 from both sides. That tells me that I need an integral of velocity from 0 to t that will equal 0. And as we just found, that will happen at t equals 6. So a couple extra steps, but some students may be more comfortable thinking of it this way.